Hello everyone, my name is Matheus Andrade, and this is a 5-minute summary on the ideas in network tomography discussed by first one. Let's start by considering a network of classical computers interconnected by classical routers. The goal of network tomography is to infer link metrics from end-to-end measurements performed by probe messages exchanged between classical computers, under the assumptions that the links are symmetric and that the metrics of interest are additive in the links. The focus of network tomography has been on describing conditions under which link metrics can be inferred, as well as describing optimization problems that prescribe the number and the location of monitors that need to be inserted in the network in order to optimize the process of inference. We decided to start mapping classical network tomography to quantum network tomography by investigating link-level entanglement metrics. In the context of a quantum network, we can think of the process of distributing entanglement between two edge nodes of this network. Our initial setting is to be able to characterize the ability to distribute entanglement in a given quantum network by only having access to its edge nodes. This means that we are only allowed to perform measurements or operations in the edge nodes, and we're not allowed to touch on the switches. We can consider this really simple quantum network formed by a triangle mesh of quantum switches that connects three quantum hosts A, B, and C. We assume that the switches are lossy such that the operations have a success probability. And we also assume that channels are lossy and transmissions are also probabilistic. We can think of these probabilities to create a model that describes the process of entanglement generation and then ask where should we start performing entanglement distribution in order to be able to characterize entanglement distribution, and also to ask what set of metrics is actually sufficient in order to recover all of the probabilities in our model. To give you an example, let's consider this single switch interconnecting three hosts A, B, and C. Here in this case, our goal is to compute the probability of generating an entangled pair in the network by only looking at the probability of distributing an entangled pair between two end hosts. We can describe the process, let's say, of distributing an entangled pair between A and B with an equation that is the product of three probabilities. The probability of generating an entangled pair between A and the switch, which would denote P sub A, the probability of performing an entanglement swapping in the switch, which would denote as P sub B, and the probability of generating an entangled pair between the switch and B, which we refer to as P sub B. If we repeat this process for all three pairs of nodes connected to the switch, we will have three product equations that can be linearized by applying the logarithmic function on both sides of this system. Then we can look at our linear system and ask, is this set of three measurements sufficient to completely characterize entanglement distribution in the switch case? And the answer is no, because this linear system does not have a full rank. If we want to be able to compute the probabilities we're interested in, we need to add a fourth equation, either in the form of an assumption let's say assuming that the switch is perfect, and hence the swapping probability is actually 1, or by thinking of a fourth measurement, let's say measuring the probability of creating an entangled pair between a host and itself going through the switch, which gives us a fourth equation to complete the ring cover system, and then successfully employ our entangled network tomography process. On the behalf of the Thrift One team, I'd like to thank you for your time.